Physics is all about the motion of things, how planets and stars move, how electrons and protons move, how the movement of molecules results in emergent properties like temperature, and so on. The role of relativity in physics is to study how that motion looks from different perspectives. Here I'm using relativity in a general sense to mean from any different possible perspective, moving, accelerating, or otherwise. Special relativity in particular is concerned with how motion looks just from a limited or special set of perspectives, which we'll get to later. But either way, relativity, special or not, is about how the motions of things look from different perspectives. Like if you were looking at the Earth and the Moon, depending on where you were and how you were moving, it might look like the Moon is moving around the Earth in a giant circle, or back and forth on a straight line, or that the Earth and Moon together are tracing out a spiraling path through space. But if the motion of the Earth and Moon can be described in such different ways, what does any one of these descriptions actually tell us about the Earth and Moon? Is one of them right and the other's wrong? Is there some preferred perspective for observing the Earth and Moon that gets the closest to the true description of what's happening? It's the goal of relativity to answer these kinds of questions. In fact, relativity can essentially be summed up as two basic ideas. One, to figure out how objects and their motion look from different perspectives, and two, to notice which properties of objects and their motion don't look different from different perspectives. We've already given an example of number one, with different ways the motion of the Earth and Moon can look from different perspectives. Number two, the idea of finding things that don't look different from these perspectives, that's a little trickier. In the Earth and Moon case, for example, all three perspectives appear quite different, but after a while you might notice that regardless of the perspective, the maximum physical distance between the Earth and the Moon appears to be the same. So you might say, aha, there's something that's independent of perspective. Maybe it's a fundamental property of the Earth-Moon system, and not just an artifact of my particular point of view. And this is why relativity is so important in physics. By studying what changes and what doesn't about a physical system when you change your perspective, you're zeroing in on universal truths. Literally. Facts that remain true from many perspectives throughout the universe, like perhaps that the distance between the Earth and Moon is 384,399 kilometers, are literally more universal than a fact that only holds true at a single place and time, like that the angle between the Moon and Earth is 150 degrees. Relativity is a way of thinking that helps you to evaluate how universal a given truth is. Okay, enough philosophizing. To make all this tangible, we need a rigorous way of describing moving things and of describing changes to how that motion looks when you change your perspective. We're ultimately going to build up to special relativity, which has to do with motion over time, but we'll start with non-moving things just to get a sense of how intuitive relativity can be. You're probably familiar with specifying the position of a cat on a plane using XY coordinates. This cat is 3 tick marks to the right of our point of reference and 2 tick marks up. So we say it's at position x equals 3 and y equals 2, which typically gets written as just a pair of numbers like 3, 2. However, 3, 2 is not a universal truth. I mean, it's just based on where I'm standing and how I'm oriented. But over here, where you are, maybe you're rotated by 30 degrees and you made the tick marks closer together, and suddenly the cat is at a different position. X equals 9, y equals 9, even though the cat hasn't moved. In fact, it's possible to specify the cat's position using any x and y values we want, depending on our point of reference, which corresponds mathematically to where we put our axes and how we orient and scale them. So clearly, specifying the position of something is not a universal truth. Or in relativity parlance, position is relative. A more universal or absolute truth can be found if you have 2 cats. Let's say they're at x equals 0, y equals 0, and x equals 5, y equals 0. I'm not going to draw a person at the origin of the axes from now on, but you should remember that the axes we use represent a particular perspective and orientation from which we measure things. The distance between these 2 cats is clearly 5. They're at the same y value and their x values differ by 5. If we move and rotate our point of reference now, the cats are at positions x equals 1, y equals 1, and x equals 5, y equals 4. So they differ by 4 in the new x direction and 3 in the new y direction. But the overall distance between the cats, which we can find using the Pythagorean theorem, is the square root of 4 squared plus 3 squared, which is the square root of 25, which is 5, which is the same distance we calculated with the original axes. This turns out to be a general truth. On a plane, the distance between 2 things doesn't change if you change your perspective just by shifting your point of reference or your orientation. I like to think about this as similar to how if I take a piece of paper and slide it around and rotate it, I haven't actually changed anything on the piece of paper. Or in relativity parlance, distances are absolute. The geometric intuition for this is that you can move your axes around, slide them up and down, and rigidly rotate them, without affecting your description of the distance between two things. If you like, we can make this mathematically precise by calling the original coordinates x and y, and the new coordinates x new and y new. Then when we've slid the x-axis an amount delta x, technically called a translation by x, we say that x new is equal to x minus delta x, and when we slide the y-axis by an amount delta y, technically called a translation by delta y, we say that y new is equal to y minus delta y. The minus sign is here because if you've slid your origin point closer to something, its new x and y coordinates will be smaller. Changes of orientation are a little fancier, but it's really just some algebra. If you reorient the x and y axes counterclockwise by an angle theta, the new coordinates look like x new is equal to x times cosine theta minus y times sine theta, and y new is equal to y times cosine theta plus x times sine theta. And if you want a fun algebra exercise, you can use these equations, or even their 3D counterparts, to check that indeed the distance between 2 points doesn't change when you slide or rotate your axes. But the messiness of all the details here really clouds the simplicity of what's going on. The important geometric idea I want you to remember is that rotating and sliding axes doesn't change the distance between 2 points. However, the distance between 2 points does change if we're allowed to change the spacing of the tick marks. If when we change our axes we also double the tick marks, then the distance between the cats becomes 10, not 5. Turns out distance, measured in numbers, is not so universal. But there is a more universal truth. Suppose we have a stick that's 1 tick mark long, according to the original axes. Conventionally, this thing might be called a meter stick, and now we can say that the two cats are 5 sticks apart. When we again move and rotate our axes and change the spacing of the tick marks, the cats are again 10 tick marks apart, but the stick is also now 2 tick marks long, so the distance between the cats is still 5 sticks. This is an example of an even more general physical truth. The distance between two things, measured in terms of another physical thing, doesn't change when you change your perspective by shifting your point of reference or orientation or the spacing of your tick marks. In relativity parlance, we'd say that the ratio of two distances is absolute. Or basically, if you want to actually describe a distance, you can't just specify a number, like I'm 5 away from you. You have to say what you're measuring distance in terms of, and what number of those things your distance is equal to. This is kind of a subtle point and very important if you're interested in metrology, the study of measurement and units, but because it doesn't really play a major role in special relativity, from now on I'm going to be a bit sloppy and just assume that whenever we're talking about distances, we're talking about distances not as numbers, but in terms of some reference distance, like meters, or cats, or whatever. And the same will apply to times. When we talk about a time interval, we'll assume it's a time interval in terms of some reference time, like the second, which brings us to the motion of objects over time. To describe a moving object, it's customary to use a horizontal coordinate axis for the left-right x position, but instead of using the vertical axis to represent height y, we use it to represent time t. So for something not moving, something that stays at the same position x at time t equals 0, t equals 1, t equals 2, and so on, we draw a straight vertical line through x. For something moving 1 meter per second to the right, we draw a line that goes 1 meter to the right for every second that transpires vertically. It's important to note that we're not saying that the object is moving through 2D space along a 45-degree line. The object is moving purely one-dimensionally along the x-axis, and we're just showing those different one-dimensional positions as time passes. This whole time on the vertical axis thing can also be a bit weird at first, since in most other situations, you've probably encountered time plotted on a horizontal axis. But vertical time has its merits, and more importantly, its convention at this point, so it's worth getting used to. I like to think of each horizontal line as representing a different snapshot of a scene. We could show the snapshots one after another as time actually passes, of course, but it's useful to be able to see all of the snapshots at once. So if we display each snapshot at a consecutive vertical position, we get a nice representation in a single static image of motion that normally takes place over time. This geometric way of representing motion over time is called a space-time diagram, and it's so central to intuitively understanding relativity that it's worth doing a few more examples. Say we have a cat attached to a spring, bouncing back and forth, left and right. If we plot this motion on a space-time diagram, as time passes, we see the cat move left and right, leaving behind a trace in the shape of a sine wave. On the other hand, if we're given a space-time diagram and want to recover the motion of the cat, we simply slide the diagram downwards at a constant rate and move the cat left and right so that it follows along the traced out path. This is important. A traced out path in a spacetime diagram is a faithful recording of an object's motion. And these paths are called world lines, presumably because they show where in the world the object has gone, though by world we often mean room or solar system or universe. Any particular point on a world line has coordinates t and x, which we write as a pair telling us for time t what position the object was located. So far, we've just been representing one-dimensional motion on our spacetime diagrams, just one spatial direction the object is moving in, and then time as the vertical axis. If we want to use a spacetime diagram to represent motion in 2 dimensions, like the moon orbiting the Earth, we actually need 3 dimensions to do so: the 2 horizontal directions for the moon and Earth to move in, and the vertical direction to trace out the snapshots as time passes. It's pretty cool. But if you have multiple particles moving complicatedly, this can get really messy on a 2D screen. And it's physically impossible to make a full spacetime diagram for 3-dimensional motion because you would need 4 spatial dimensions to do so. 3 horizontal directions for the motion and a vertical direction for time, which of course is impossible in our universe with its measly 3 spatial dimensions. So physicists normally restrict their spacetime diagrams to just 1 or 2 spatial dimensions and time going vertically. So, how does relativity work with spacetime diagrams? That is, now that we know how to describe motion geometrically, how do changes in perspective affect that description? Let's take as an example me staying put right at x equals 0, and a cat moving 1 meter per second to the right away from me, starting at time t equals 0. It may not surprise you to notice that when you slide the x-axis to the left or right, the particular x positions that the cat and I have at any particular time change, but the distance between us doesn't change. At time t equals 0, we're still 0 meters apart, no matter how much you slide the x-axis back and forth. At time t equals 2, we're 2 meters apart, and so on. So you can slide the x-axis back and forth however you like, and spatial distances don't change. Similarly, if you slide the time axis up and down, absolute times, like when the cat starts moving away from me, change, but time intervals don't change. The cat still takes 2 seconds to get 2 meters away from me. So you can slide the t-axis up and down, and distances in time are left unchanged. If we have 2-dimensional motion, then changes in the orientation of the 2 spatial axes also don't change the distances between objects at any particular time. Essentially, you can reorient the xy axes however you like. So the relativity that we applied to purely spatial diagrams applies pretty well to space-time diagrams, too. To summarize the major takeaways, relativity is about understanding how changes in perspective do or don't affect motion. We can describe motion over time geometrically using spacetime diagrams, and spacetime diagrams can help us see how changes of perspective affect how the motion of objects looks. Like how changing your position and orientation correspond to sliding the axes around and rigidly reorienting the spatial axes, without changing the spatial distance between 2 points at the same time, and without changing the temporal distance between 2 points that are at the same location in space. However, all of this relativity is static, and by that I mean we haven't yet talked about how motion looks from a perspective that is itself moving. That's ultimately the key to special relativity, and will be the subject of the next video. If you'd like to play around with some spacetime diagrams yourself, I highly recommend checking out the Propagation of Light interactive quiz on Brilliant.org, this video's sponsor. This quiz is seriously cool. It uses spacetime diagrams to guide you through how astronomer Ole Romer deduced that the speed of light must be finite just by observing the orbit of Jupiter's moon Io. It's a super clever idea, and the quiz does a great job of using spacetime diagrams to visualize the situation and guide you through calculating the speed of light yourself. In fact, this quiz is part of a whole course on special relativity that Brilliant has available at brilliant.org/minutephysicsspecialrelativity. And doing problems like theirs after watching videos like mine is a great way to practice and really internalize the ideas of special relativity. If you decide to sign up for premium access to all of their courses and quizzes, you can get 20% off by going to brilliant.org/minutephysics. Or even better, go to brilliant.org/minutephysicsspecialrelativity, which lets Brilliant know you came from here and takes you straight to their relativity course.